Okay, so let's start by the basics. The thrust of a rocket is a force, which is equal to ma. And we know from my thrust video that this is also equal to m dot, which is the mass flow rate, times v equivalent. Let's rewrite ma and m dot v equivalent. M dot v equivalent is dm over dt times v equivalent. And ma is m times dv over dt. Now, we have a lot of d's and stuff all over here, so let's try to get rid of them to simplify this equation by integrating on both sides. So that will look like v equivalent, which is outside of the integration because it's a constant, times the integral from initial to final of dm over dt times dt, which is equal to m times the integral of initial to final of dv over dt times dt. Now let's move this m to this side of the equation. So we'll rewrite this as the equivalent times the integral of initial to final of dm over dt times m on the bottom times dt, which is equal to the integral from initial to final of dv over dt. Now these dt's cancel, so times dt. So these dt's cancel on this side, and these dt's cancel on this side. So we're left with v equivalent times the integral from initial to final of dm over m, which is equal to the integral from initial to final of dv, and the integral of dv is just v because this integral is adding up all the little dv's. Or to be more specific, it's v from initial to final. And that's equal to v equivalent times the integral of, or from initial to final, of 1 over m dm. And we have this 1 over m here, and the solution to an integral that is 1 over m, or 1 over x, we can see here on this integration table, is the natural log of x. So here we can rewrite this as v equivalent times the natural log of m from initial to final, and make that equal to v from initial to final. And v from initial to final is the same thing as saying v final minus v initial. So this is just the delta v. And delta v is equal to v equivalent times the natural logarithm of m final minus the natural logarithm of m initial. And due to a rule of logarithms, this subtraction, final minus initial, is the same thing as the natural logarithm of m final over m initial. And that's the rocket equation that you might have seen before. Delta v is equal to v equivalent times natural logarithm of mf over mi. Now, previously in my specific impulse video, we discovered that specific impulse is equal to V equivalent over G. So we can substitute into this equation a specific impulse, because V equivalent is equal to specific impulse times G. So let's just rewrite this. Delta V is equal to specific impulse times G times the natural logarithm of mf over mi. So these are just two different ways of looking at the rocket equation, and they'll come in handy later on. In this example, we derive the rocket equation using force, but you can also derive it using the conservation of momentum, which might be a little more intuitive. So here we have a rocket with all the fuel inside of it, and it hasn't started burning its engines yet at time t. And at time t plus dt, or a tiny little increment of time in the future, it does start burning its fuel, and the amount of fuel left inside of it starts to decrease. At time t, the mass of the rocket was just m, which included the mass of the fuel and included the mass of the rocket itself. At time t plus dt, the mass of the rocket is actually m minus dm, which is the tiny amount of mass that left the rocket over this tiny little amount of time. We can just call the mass of the exhaust dm. The velocity of the rocket at time t was just v. Now at time t plus dt, the velocity has increased v plus dv, and it got this dv from burning some propellant backwards. Newton's third law, every action is an equal and opposite reaction. It burned and it gained some velocity. So the velocity of the exhaust we can call dv. According to the conservation of momentum, this system's momentum must be the same at time t and at time t plus dt. So what is the conservation of momentum of this system at time t and at time t plus dt? Well, at time t, the momentum is m times v. And that's equal to the momentum after, and the momentum after is a combination of all these little things. So it's m minus dm, it's the mass, times v plus dv, the velocity, plus the momentum of the exhaust, which is dm times v of the rocket minus ve, or v exhaust. So now let's expand this a little more so we can separate all the little components. Let's distribute this. So mv equals mv plus mdv minus dmv plus dmdv plus dmv minus dmve. So now let's simplify this and cut out terms. mv and mv cancel. Negative dmv and positive dmv cancel. And dm times dv, well, this is a tiny change in mass times a tiny change in velocity. So something tiny times something tiny makes it become even smaller. So this just practically goes to 0. So we can sort of forget about it. So we're left with negative m dv is equal to negative dm times ve. Since we have negative on both sides, they just go away. And we're just left with m times dv equals dm ve. So now let's move the m to this side of the equation. So we get dv equals ve times 1 over m times dm. Now we have d's here on both sides. Let's try to get rid of them. And we can do that by integrating on both sides. So let's integrate from v initial to v final of dv times dt, and let that be equal to ve, which is a constant, which is outside the integral, times the integral of m initial to m final 1 over m dm. And we just get for, on this side, the delta v, or v final minus v initial, that's what this integral comes out to be, is equal to ve times, and we can see back onto our integral table that we already used before, the solution to 1 over something d of that is the natural logarithm of it. So this is times the natural logarithm of m from m initial to m final. And we know from before that these being subtracted makes the delta v is equal to ve times the natural logarithm, if we have the m final minus m initial, which is what this is saying, then we can rewrite that, since it's a logarithm, as the natural logarithm of m final over m initial. And that looks just like what we got before, except that before we had a v equivalent, which is the more accurate representation because that encompasses the whole thrust equation. So let's just substitute this with v equivalent. So they are both equal. These are both two valid ways of describing it. As a quick side note, when you equate MA to M dot V equivalent, V equivalent is a vector, and that vector is in the opposite direction of the rocket. So to account for this, or to show that, we have to have a minus sign here that will represent the direction of the vector, keeping this thing in absolute value and not using vector notation. And this stays in the whole derivation, and in the end it actually flips the ratio of m final to m initial to m initial over m final. And this is the ratio that you normally see in many different graphs, like this one that plots the mass ratio of the rocket over its specific impulse. Now, mass ratio in this case just means the mass initial, which is the mass of the rocket fully fueled on the launch pad, divided by the mass final, which is the mass of just its payload and whatever rocket is left without the fuel in it. So we obviously want MF to be as big as possible. So how do we do that? By making the specific impulse as high as possible. For example, if we want to reach 10,000 meters per second, or the payload to reach 10,000 meters per second, which is about just under what it takes to get into orbit, which is about 11,000 meters per second. If we have a specific impulse of 200, we're going to need an absurdly big mass ratio to get there. So the amount of payload we'd be carrying is about 1%. But if our engine has a specific impulse of about 400, then our mass ratio will be about 12, and about 8% of our rocket will be payload, which is much better. And for example, the Saturn V second and third stages had a specific impulse of about 421. So in this video, I explained the rocket equation by deriving it and explaining how engineers use it in the real world. I hope you enjoyed this video and learned something, and please like, share, and subscribe.